Hello everybody, this is my first ever YouTube video. I hope this is informative and insightful and people derive a lot of useful information from this. So today we're looking at differences between classifying models and regression models. Classifying models are models where we're working with labeled data. So think of things like small, medium, large, extra large, or if it's types of fruit, it could be watermelon, grape, banana, apple, cherries, things like this. Things that have a description and a label, and regressors are used for continuous data. So labels are discrete and they can be put into defined buckets. Continuous data would be like stock market data, temperature, measurements and feet and inches and centimeters and things like this. So even if you want to consider weather classifiers would be things like rainy, snowy, sunny, windy, things like this. And a weather regression model would measure temperature changes. So 71 degrees, 71 and a half, 72, 73, 74, 75, things like that. You can see some use cases right here for classifiers for spam detection, fraud detection, image recognition, medical diagnostics, but there's all kinds of other things too. There's all kinds of varieties. And for regressors, we have house price prediction, stock price forecasting, sales forecasting, temperature prediction, like I just alluded to a moment ago. So let's get into a couple of these models. I have some data saved on my laptop here. I'm going to run this model so you can see how this works in real time. I'm going to share this code with everybody. It'll be posted with the video on YouTube. I'll share all this code so you have it, so you can copy and paste it and run it for yourself. And I'll show you the data source at the end. So here you can see the different features in this data set that we're working with. This is classifications of wine, types of wine, and then the class that the wine belongs to based on these features. So we're going to look at all these features. These are the columns in the data set, and then try to make a prediction into which classes this wine belong to. Class 1, 2, 3, so on and so forth. You can see the data here. Here's a scatter plot of the data so we can see how everything looks visually. Go down a little bit. We're going to run our first classifier. Again, I'm going to share all this code with everybody. This is done in real time just so you can see the results. So 0.972, this x variable right here, sorry, is coming from all of these features right here, all these column names that you can see. These are the independent variables, and then the dependent variable, which is dependent on the independent variables, is the very first column right here. It's called class of wine. So 1, 2, 3 is the class, and then all of these other variables are being used by the independent x variable right there. So you can see this first model made a prediction of 0.972, so pretty close to 100%. It says pretty accurate, 0.972. I'm going to run it again. This is my Jupyter notebook here, running this in real time as we go. Control Enter once you click on the cell, runs the code. So 1.0, okay, so we got perfect prediction based on this add a boost classifier. These classifiers over here are slightly different types. They're doing something different. This is a random forest classifier. This is a decision tree classifier. So the objective here is just to try several different models and see which one is giving you the best performance. Once we get to 1.0, we're pretty much done here. We've got a classifier called the Add a Boost classifier that's making perfect predictions. So once the CLF is the name of the model that I'm giving it, see CLF equals Add a Boost classifier. Now it can make predictions based on those features that I just fed it. So if you look closely at the data, you'll see alcohol, maltic acid, so on and so forth, all the way to proline acids. And that is what we're capturing down here. Once we've trained and tested the model, we can use it to make predictions. These are the predictions, and it's saying this is class type 2, okay? So this model is working basically perfectly. We're getting 1.0, 100% accuracy for this add a boost classifier. So that's pretty cool. This is a gradient boosting classifier, not performing quite as well as the add a boost, so we'll leave that one alone. 0.94, so close, but not 100%. This one's 91% accurate. Here we see another 94%. And we'll test another one down here, 58%. We'll stay away from that one. It's not good at all. Here's 83%. That's decent. Anything over 70% is decent, but again, if we can get 100%, that's really what we're aiming for. Now let's move on to regressors. Again, I have a data set saved on my laptop here. This is house data. I'm going to go ahead and run it, load the data. do a little bit of cleanup, any kind of string replacing with commas. We're going to replace with, or comma with a blank space after it. That's kind of garbage data. We want to clean that up. So we're going to just get rid of those commas and leave nothing in its place. So we've done that. Convert index value to ints. So just making sure that the data type is the correct data type. We have ints, floats, which would be data with decimal places. We have strings, which are words, all kinds of different data types, right? So we want to make sure that we're working with the correct data type. Here's the data that we're looking at. Information, Z address. This is just basically the cleanup address. Bathrooms, bedrooms, square footage, last sold date. So all kinds of data relative to real estate, even latitude, longitude, and then the neighborhood where this property is located. So pretty useful information. We're going to take all this again, feed it into some models, this time regression models, and we're going to do essentially what we did before with the classifier. So I want to do a quick plot of the data so I can see what things look like. I don't think I need the latitude and longitude plotted. That's not super helpful in this case. It could be in other cases. But the more interesting thing to me is the number of bedrooms. You can see it's kind of skewed between about 2 and 4. So most of these houses have between 2 and 4 bedrooms. Bathrooms, kind of the same thing, up to 5 bedrooms, up to 5 bathrooms. There's a couple houses with a little bit more, but not too much more than that. And most of these houses are pretty small, maybe several hundred square feet, up to about 5,000 square feet. And it looks like we have one that's 25,000 square feet. That's an outlier. So we captured that. That's interesting to know, but you can see like most of the houses are concentrated within a few hundred square feet up to 5,000. Even once you get to 5,000, there's just a handful there. So let's move down. We can see the data again. Now for the Y variable, we're going to say last sold price. I want to try to predict the price of this house based on these independent variables. So again, the dependent is the Y variable, the independent is X. And just like we saw with the classifier, it's based on the bathrooms, bedrooms, finished square footage, latitude, longitude. That will show you the neighborhood, total rooms, year built. Z estimate is the Zillow estimated price. Z index value is a value that Zillow calculates by itself, and then the zip code where the property is located. So again, based on all the independent variables, I'm doing the training, testing, splitting, starting with a linear regression model and trying to see how well this model can learn and make predictions. We're seeing as it runs in real time. Oh, we got an error here. Found variables, inconsistent number of samples. You know what? I think I know why. I have to run every piece of code in between. Okay, we did load it. Let me run the plot. I don't think that's causing the error, but I think it's picking up the X and Y from the classifier. That's what happened here because I didn't refresh this and load everything. So sorry about that. Apologize. This will fix it. Okay, so we have 0.71 accuracy. So over 7%, 70%. So that's decent. We should probably be able to get a little bit closer to 90, 100%, like we saw with the classifier. We did get perfect training and testing with the classifier. We're gonna try to get a model that's a little bit more precise over here. And just before we do that, let me mention one quick thing about the R squared. The R squared is the goodness of fit for the model over the the data set. So how well do the data sets, how well do the data points align with all the average data points? So the R squared is going to show us that, how well the model is fitting to the data. That's very important. Again, the closer we get to 100%, the better. But an even more accurate metric that we can use is called the adjusted R squared. The adjusted R squared does provide like a small mathematical correction right here. You can see how this is done. Again, I'll share all the code with everybody at the end of this. The adjusted R squared is a slightly better metric because as you add more and more features to your data set, the R squared will automatically increase, even if the features aren't useful and helping the model to learn and train and become tested and make predictions. As you add more and more features, the R squared will always increase, but you only want to add features that are going to be helpful. And we have another video about this. This is called feature importance. You only want to add features that are actually going to help you to make more accurate predictions and not just add features just for the sake of adding features. But you can see that the R squared here is just slightly better than the adjusted R-squared. The adjusted R-squared could be equal to the R-squared, but most likely it's going to be slightly less. In this case, it is just like a fraction of a percent lower, and that's exactly what we would expect here. So again, this is a mean square error and the mean square error and the mean absolute error. So this again is going to show us how accurately this model is learning and how precisely it can make predictions. And this is looking at the overall housing price. So the price swing will be close to half $500,000, right? And some of these houses are millions and millions and millions of dollars. So you're going to see a big skew there. But again, the smaller these numbers, RMSE and mean absolute error, the better. And we can see this model is just okay. It's not super tight. It's only 71% accurate. We want to get try to get closer to 100%. So here's the next model. This is the decision tree regressor. I'm going to run this 0.6%, so only 60% of the time it's correct. That's not very good at all. This one, let's run it. Let's see what happens. Okay, we're looking at what now? Probably 78% accurate. Okay, so it's getting a little bit better. And these are just different models that we're trying, right? So here's the nearest neighbor. This is the name that I'm assigning to this. Here's the random forest regressor. The naming convention can be anything. The more intuitive and the more meaningful it is. But you can literally name it anything. There's 0.65%. Let me run this just to see if there's any changes or updates. 0.71, 0.77. I think that's what I'm seeing here. 0.77%. So these are okay. The best performing is probably 78%. And these are not all the models. I have another video that I'm going to do shortly to show you how to loop through all of the models in one quick go. This is just comparing the results between classification models and regression types of models right here. So we're getting towards the end. Like I just mentioned, there are two links you can take a look on my website. This is PyCaret and Lazy Predict. These are two tools that will automatically loop through about 40 different classifier models and 40 different regressors, so you can see which ones are performing the best, and it will give you some of the details that you saw above, the R-squared, the mean absolute error, some metrics like that, so you can understand which models are performing the best. There's one more thing I'll go through at the end here to show you visually a decision tree and how it's plotted out and printed. Again, the dependent variable is going to be the y. The independent variables are the x variables, right? So this is a visual of the decision tree of how this model is performing. This is a classification model. You can see how the features are over or under a certain amount, and then what sort of buckets these branches of the trees will go into, and then visually how it's all plotted out. This is how the model is making these types of decisions and then ultimately making predictions, right? So we can see the Gini impurity, the values that's generating. We want impurities to be smaller and smaller as they continue, and then this branch will continue on. If the impurity is larger and larger, it's not learning very well, and the model's just going to stop, right? By default, it's going to stop learning. So there's a classifier. Here's the regressor doing the same thing. Again, all this time we're getting data from online, so it's not coming from my laptop. But this online data is for continuous variables, so it's all regression. These are number of cylinders, horsepower, weights, gears, carburetor for cars, and we're trying to predict the miles per gallon once we have the independent variables. The dependent variable that we're making predictions on is miles per gallon. Again, this is a visual representation of how that regressor is working in the background and how it's making the decisions. So here's the data source right here. I'll share this with everybody at the end of the video. And there you have it. I think you have everything you need to compare and contrast different classifying models and different regression models. And we explained the R-squared, the adjusted R-squared, and the visual random forest decision tree plotted out in a graph format. Okay, so that's the end of the video. Hopefully you guys found this interesting, useful. I'm going to come out with a lot more videos, and yeah, hopefully I can continue to drop knowledge and help people to get more educated about data science, machine learning, deep learning, artificial intelligence, business intelligence, and things like this. So thanks for your time. Have a great day. Bye.